which is on simplifying big data management with Apache Falcon by Srikanth Sundarrajan. Srikanth works at InMobi Technology Services, helping architect and build their next generation data management solution. He is the brain behind Apache Falcon and has shepherded the project from identification to top level project at ASP and currently VP of the Apache Falcon project. He has been actively involved in various projects under the Apache Hadoop umbrella, including HDFS, MR, and OZ. Please welcome Srikanth.
Thank you. So I think he completed the introduction. So I've been working on this big data space for a while, roughly about 7.5 years. Been with Yahoo earlier, Sharad and I and Retry, many of us are colleagues. So I've been working with InMobi for about 4 years. So we've been trying to get the data platform set up there from the very beginning. So as part of the journey there, we built multiple tools, and one of them is Apache Falcon. So I will kind of give a good overview about the project, its architecture, and the case study probably as an example for us to go through. But before that, I just wanted to quickly check how many of you kind of run Hadoop jobs in production, because depending on that, maybe I'll spend a little more time in the background and context and less time on the details. But if people are already familiar, then I'll spend more time in detailing out the product itself. So how many of you run Hadoop in production? So one, okay. All right. So just the people who are used to this have to bear with me because I'll just try and spend a little more time, going over the background. Just let's take a example that we can all relate to. And Sharad earlier in his talk, he said that all things web and mobile are essentially generating too much data that they end up on a big data platform, so they have to be processed there. So we'll take an example, in that space, a social app. People may be familiar with Facebook or Twitter, things like that. So we'll take an app similar to that. So essentially, what we all do is kind of log into the app and access the app. So let's categorize them and call them visits. So you visit the app, visit different pages, different content. Go to view. You can go post what you want to post there on the social media content. You probably like what others have put. You comment on stuff. Based on what you have done in the past, the system may be recommending things to you. These are things that we're all familiar with in our own life, everyday life. We use these apps all the time. So let's take this as an app as an example. So if you have a large user base for such an app, what this would mean, let's say we have 50 million users for this app. Whenever users log in every single day, they're going to be going to different parts of the app. And let's say a user engages for 10 minutes, that's going to generate a lot of traffic. The traffic is in the form of visits. So you go to this page, the system is recording this information saying that you've visited that page at this time of the day, from this location, from probably using a Wi-Fi network or on a 3G network. You're accessing it from an iPhone or a Nexus, so whatever it is. So the system is actually recording this information in the form of logs. People might be familiar with systems like Kafka, which is used to stream this data, collect this data, and store this in Hadoop. So what do we do with this data? So the user visits, for instance, or posts, for instance, or comments, things like that. What do we do with this data is to analyze this data, and because that's the primary corpus on which this social app is actually based on. So you would want to see, is my app equally popular as it was yesterday? Meaning, how many users are visiting this app on a daily basis? What time of the day are they visiting? How long are they staying in this app? How many posts do they make? how many likes or comments are they making in the app. So how many people are they connected with. So how is the network growing. So the social media company, for instance, would want to be able to analyze all this and summarize this and watch what's actually happening in the business. And if it happens also to be a monetization platform, so for example you put ads in there, let's say Yahoo homepage, for instance, you go there, you have ads there, and the ads are monetizing for you. So you have to figure out how many people are clicking on those ads, what's the revenue that you're making on those ads, and stuff like that. So all of these are generating tons of traffic, and they land up in your system. So for a minute we will assume that they magically appear, and let's not talk about that. So our focus in this talk would be mostly around, once it reaches your Hadoop cluster, what do you do with it? How do you go about processing this data? So normally in a conventional data processing world, you may be familiar with this term called ETL. So the extract, transform, and load. So what you do is you take data, you transform it, and then load it into a conventional warehouse solution, and then you kind of can do a lot of analytics on it to get what you want. In the big data space, it's slightly different. You can't use the conventional off-the-shelf products because they probably don't work at this kind of scale. We're talking about scales in excess of tens of terabytes every day or hundreds of terabytes every day that you're ingesting. So the scales are very, very different in the big data space. So hence your choice of technology and what you use to process it's got to be different as well. So if in the example that we spoke about, so we have users visiting the app, and we are recording these visits in, let's say, some kind of a log, minutely rolled up and collecting somewhere. And let's say there is a recommendation that you have made, and people are accepting your recommendation and interacting with your system. So you're recording that probably as a different stream of event. Let's say there is an ad that is displayed to you, and let's say you are recording that information of what ads are being shown to this user also in a different stream. So you have different streams of data that you are collecting and maintaining in your Hadoop cluster. Now what you do with this data, depending on the use case, let's say I want to count distinct users who have visited the site today. So you take the visits data, you must obviously have an identifier which identifies who the user is. So you're probably going to, in a SQL world, probably just going to run a select distinct user ID count of that and get the unique users for the site today. So that's very, very simple if you were to think in SQL. So in the big data space, you might do something similar or equivalent in a language like a Pig or a Cascading or a Hive or even a native MapReduce application. So once you do that, you basically get unique users. Now let's say there is a subsequent processing that you need to do to take these unique users and do something else. So you basically end up with a pipeline of applications. You end up with some data reaching you, and then you do some processing on it. You enrich it in some form, and you create a new data set, if you will, and that new data set has different kinds of information compared to the original one that you process. So the visit data you transformed into unique user count, for instance, in this particular example that I was saying, and let's say you took that data and started doing a trending report on top of it. That data may look different. So what I'm trying to kind of drive is data land on the cluster in some form, and then you transform that and derive new data sets out of that, and that data set can further be refined, processed, and produced into another version or another instance of data set. So essentially what happens is that you have a DAG of sorts which is giving you a pipeline of what is actually happening in the system. So you basically have a piece of data that is getting transformed into something else, that is getting transformed into something else, and so on and so forth. And to give you another example, if that makes sense. So we talked about the visits being collected every minute and rolled up into a minutely bucket. So for us to count unique users, we have to consider all the 1440 minutes in a day to figure out what are the unique users for today. But let's say I wanted to count the unique users for a month. You might obviously understand that unique users are not additive. So you had 5 unique users today, 10 unique users the next day. The cumulative unique users over the last 2 days is not 15. So you have to dedupe between them. For you to be able to dedupe them, you have to extract the unique set for day 1, unique set for day 2, and keep it in some primitive form so that you can dedupe the third day, right? So that you will be able to figure out how many appeared day 1, how many appeared day 2, and what is the unique users on day 1 and 2. So for you to be able to do that, you need to maintain intermediate states of data so that you can do that easily the following day and so forth. For example, you can get weekly unique users, monthly unique users. So it's not about just counting the unique users from that data, because if you did that, if you have to do unique users for the week, you will end up going back and reprocessing all the data for the week because you didn't create a prepared set for you to do this fast enough. Because if you didn't do that, you will be processing a large amount of data each time. And if the incoming data is significantly large, let's say you're ingesting 40 terabytes every day or 50 terabytes every day, for you to be able to reprocess all the data every single day is going to be very, very expensive. So the smartest way to do things in this space is create a pipeline such that you have intermediate temporary states of data maintained to make life easy, to simplify the I/O or reduce the I/O through the pipeline phase, spanning across days and weeks and months. All right. So that is really one of the learnings for me and many others in this space. So to be able to create this pipeline and manage it as a pipeline and create intermediate sets for you to be able to use this more effectively as you go along, as opposed to going back to the raw data and processing it all over again. This is not a very new thing. It's probably something that's been done in the traditional world as well. So you might create temporary tables or intermediate tables in the conventional world, and a similar thing kind of happens here in the big data space as well. So I have a feeling that maybe I'm a little fast, but I just wanted to pause here and ask if what we kind of discuss, does it make sense, or it's not so connecting well. It's fine. All right. So with that background, so I'm hoping that this context would have helped in kind of appreciating the fact that data processing on big data is in many ways similar to what happens in the smaller world. You have to create a pipeline of sorts and be able to process that. Intermediate states that you maintain are very useful for you to reduce I/O when you have to process data over large periods. With that, I just wanted to kind of articulate what challenges there are for us to kind of solve. So the biggest thing that comes to the top of our mind is the scheduling and orchestration. So if you have to go back here, let's say there is 2 data sets, let's say F4 and F5. So this 2 data sets are actually naturally landing in the Hadoop cluster through streaming mechanism. Let us say for some reason there were delays in this data arrival. You basically cannot kick off the processing, which is this red arrow here, which consumes F4 and produces an instance of F1, right? Which means that the scheduling is not simply wake up at 5 a.m. in the morning and run this processing, right? You have to wake up at 5 a.m. and also make sure the data for F4 is complete and ready for consumption before you kind of go ahead. Let's say another case where F5 is your static data that doesn't change often. Okay, so in this case, I want at least a most current instance of F5 that is good enough for me to process, but I don't need today's instance. So you could basically optionally work with the stale data, but it is not the case for something else. So there are these interesting scenarios that you will kind of come into. So the scheduling and orchestration to handle this stuff is one of the challenges in handling big data and processing big data. So to be able to figure out when to run something, what input should it be considering, when is it optionally okay to ignore something which is stale, when is it mandatory for you to pick the latest version, because oftentimes what you need is the data that comes late. Let's say it's coming through a learning system, you are better off with a slightly stale model that we have learned, as opposed to waiting for the most accurate one, because the stale one would still be effective, and absence of a model completely is catastrophic. So you'll have to find out what are the characteristics of the data that you are depending on, and appropriately choose the scheduling and orchestration rules that govern that pipeline processing. Now the underlying system which enables you to do that should have the capability to express these things naturally and seamlessly, right? So that's one of the things that is required. Second thing is it's a distributed system. Hadoop is built with the assumption that nodes fails, so it's supposed to work around it. Occasionally jobs do fail, even because of node failures or even otherwise. Jobs do fail, and sometimes it fails in a transient fashion, sometimes more permanent, sometimes due to systemic issues and stuff like that. So you got to have a strong, robust failure handling mechanism to make sure that you're reprocessing what you have, what has failed, but keep it to a level where it is not expensive. For example, I can't have a very, very coarse grained processing unit that makes reprocessing very expensive. For example, if I were to process a very large set, and along with it I'm computing few more other stuff, while the major process is complete, let's say it took 10 hours to complete that, and that is over, and then you have subsequently 2 small steps to finish, and that takes 5 minutes each. Let's say one of those 5-minute steps fails, you can't go back and retry the 14-hour or a 10-hour job all over again, because it's very, very expensive to do so. So the right level of handling these failures, and what level should you do, with what scope should you be handling these failures, is very, very important and essential in the big data space, because the job run times can be in the order of hours, especially if the input sets is very, very large. So you can't afford to have completed work repeated because of some downstream actions being partially complete or incomplete. So you can't afford to go and recompute and waste cluster resources, and also miss your job's SLAs, if you will. Data transfers and eviction are standard data management functions that you will kind of need. So if you have a primary cluster where you are generating this data, you need a secondary cluster on which you have to back this up for, let's say, a business continuity reason. So that's one reason why you will transfer data from one location to another location. There may be cases, there will be cases where you will have to delete data after it's old enough, after it's aged enough. So if I am ingesting 40 terabytes a day in a single year, I'm going to be in excess of 12 petabytes, right? So I have to make sure that data that is not necessary is thrown away, and data that is useful is kept and retained in the system. So the eviction has to be implemented through policies effectively by the system without having to repeat these capabilities multiple times. Archival of data that is that you have ingested into your system, data that you have processed, you want to keep it off storage and keep it in some low cost storage, is a use case where you would which is common in the data management world. You will also have scenarios where change has to be managed. For instance, you took your input set and you processed it and you produced a new data set or a instance of data. Now for some reason the output is incomplete or incorrect, you'll have to reprocess that. Now there are downstream applications here, let's say F4 is processed and you generate F1, and for some reason F1 has to be regenerated. If F1 is regenerated, all downstream flows parts like F2 and whatever is down further below have to be reprocessed if that is essential. For example, if this is a very, very critical metric that is being computed in this flow that you can't afford to have inconsistency, you have no choice but to propagate this change downstream entirely, right? So that is a capability that has to be natively present in the system, because whether it is upgrade of software that introduced a bug, or whether it is missing data that caused originally for the data to be incomplete or partial, whatever the reason that may be, if you have to change data and there are downstream components which are dependent on this data, and if they have to propagate the change. So that is a capability that needs to be there. Dependency and schema management it will be very, very useful if this view is visible to you at all times in your system. So if they were all not connected and visible like this, oftentimes from a debugging standpoint and for you to understand what is actually happening in your data center, it becomes very, very hard. You need to know that F4 and F5 are the entry level data sets that land in your cluster, and they are processed to produce F1, and F1 and F4 together produce F2, and so on and so forth. So this lineage of information between what is the dependency between one feed and another feed, or one unit of data and another unit of data, is kind of very, very useful to have. More from a documentation of sorts, or something that is easy for you to use to understand what's actually happening in your system. And this can also be very, very useful for debugging applications. For instance, F2 is something which is very, very critical, and you want to know why F2 has not been computed yet. Let's say in your data center today, for today's instance of F2 is not computed yet, you would want to know why. So the system would be able to tell you that F2 is not computed because it is depending on F1, which is not ready yet, and F1 is not ready because the upstream processing here is still running and running slow today, right? So you'd be able to quickly navigate up, and in a single view be able to figure out what is wrong with the pipeline and its health. So those are essentially the set of challenges, if you will, that normally one faces in setting up a big data processing system. Any questions, thoughts at this time before we move further? So this schema management is essentially talking about, so there is F4 for instance, and I want to know what is the content of F4. It should be easily discoverable. It's more like a catalog of sorts that tells you what's the content of F4, what's the content of F5 and stuff like that. So this is useful when the system becomes large. Let's say there is only 2 streams of data that comes into your system, then you're not bothered. It's fairly easy for us to figure out what's flowing in and how to kind of understand what's flowing in. But before and your company is large enough, you would have hundreds and hundreds of these, maybe thousands of these. So when you get into that situation, somebody would call the same data in 4 different names and you don't know what they're referring to. You would be wondering what is the content of the data. So it will be useful to kind of have a catalog integration to understand what's the content of the data. Not necessarily in terms of the actual data, but from a schema standpoint, right? It will be useful to kind of have. So processing engine is like I said, it's up to the your choice. For instance, in our environment we use Pig all the time. We're starting to use Spark, and in many cases we use native MapReduce jobs. But that's not so relevant from a overarching data management problem. That's more a choice depending on how debuggable is an application, how much performance do you need, how much productivity is important to you, how much testability is important for your code. So for example, if I write a MapReduce code, maybe it will take a little longer to write, maybe I'll have much more control into the framework implementations to do stuff. People who are familiar and have a liking to Pig may argue, actually that is not true, because you have to do a lot of learning to understand how MapReduce works. Pig being written by very, very seasoned MapReduce developers would actually develop it much better than what a new MapReduce developer would anyway do in a native job. But Pig in some ways will control what you can or cannot do because it doesn't expose all the primitives. People who are familiar with cascading may find the sinks and pipes flows quite convenient and easy to understand. So the choice of language that you use to process it depends on what's your priority and where your familiarity is. Yeah. Can we move on? So the rest of the talk I'm going to discuss a little bit about Apache Falcon. So this is a project that we started working at InMobi 2012. After about 6 months of development in across 2 versions, we kind of put it in production, started using it for a wide variety of applications. Then we incubated it in 2013. We graduated last year to a top level project. So a lot of people outside of InMobi are using it in production. Packaged into Hortonworks distribution if you guys are using one. So off the shelf, it's available there, and it's available for you to download and use as well. So it's currently 0.6 is the latest release. Doesn't mean that it's not stable. It's not 1.0 because we're still evolving the APIs. So once it's kind of settles down, we'll have 1.0 release. So just to give a broad perspective of what Falcon is, it basically provides very, very simple abstractions for you to do things. It recognizes the fact that there are 3 elements that you have in your big data environment. So first of all is the infrastructure. That's essentially the cluster that on which you are going to run your applications or on which you are going to store information. So that's one abstraction that it allows you to express. Next is it allows you to express what a data is, what it calls as a data set. Data set is something, or a feed is something that has a certain periodicity to it, has a certain schema to it. So that we kind of use to express data. Similarly, you can express your processing logic as a declarative function inside Falcon. So these are 3 basic primitives or abstractions that Falcon kind of exposes. So before we go into each of these, so these elements are interdependent. So you could say this data is actually stored on this cluster, and this data like we showed in this DAG is actually used for processing this processing code, and it produces this. So you basically express these as this dependency information inside through this simple abstractions. So that's all you essentially do with this system. The system is then able to use this information to solve a bunch of these problems as we listed here. All right. So what does a cluster have? The cluster essentially has endpoints that you can define in them. So you can say in this cluster, if you have to write, the write URL is this. So it would probably give a HDFS scheme URL, right? If you want to launch a job on this cluster, here is the resource manager in Yarn that you need to use. Or if in this cluster is actually present in this co-location along with few other clusters, all co-located in one place. So you basically define infrastructure element completely through a cluster entity. So this is what a cluster entity is. And you logically give this a name. So you can say this is my cluster A. So now you can say data A is actually on cluster A. You can basically give it a logical name. You're no longer talking about endpoints and port numbers and host names and stuff like that. You're talking about it in logically representing an infrastructure element. We'll see how this can be useful when we look at a case study. So just stay with me for a while. So this is what a cluster entity really is. So a feed is the second entity that Falcon natively provides in its abstraction. It's something that represents how a data is present in the cluster. It says what's the periodicity of this data. Does this data come repeatedly? If so, how often does it come on the cluster? How is it present? And where exactly is it present in the cluster? For what time period is this data valid? When did it first started flowing? Till what time is it likely to flow? It's possible that it will flow endlessly, but it's something that you can specify as a validity. Where exactly on the cluster is it present? If it's a file-based storage. If it's a table-based storage, what is the schema URI for that table? You can specify that in the feed definition. You can specify the feeds ETA. I expect this data to be present at 6 a.m. every morning. This simple annotation will help you understand if you are delayed in a particular day when you are executing your pipeline. So this is basically something that allows you to describe some metadata and annotate your data along these lines. So you can say, I want this data to be retained in the cluster for no more than a week. I can just declare that, and we'll see how that is kind of used for something else. You can say, what's the schema that this data is based on. You can also say where to archive this. If you have to archive this periodically, where to archive this. You can actually specify these properties on a data set. On a process, which is basically a compute unit, you can say when and how should I process this. What are the dependencies for this process? What inputs is this process dependent on? What does it produce as output? On which clusters am I required to do this processing? I can actually just simply say that. And going back to your question that you had, what is the application that it will use for running this process? Actually, I can write a cascading application and plug it in there and say, run this cascading application whenever this job has to be kind of run. And you can give a bunch of properties which can be used for application runtime. So the dependency will appear something like this. So your data set to your feed is dependent on your cluster, your process is dependent on cluster, your process is dependent on data set, and it can also depend on external data source which could be outside the cluster. So your dependency is somewhat represented this way in the system. So the before we move further, are the abstractions making sense? It's like a wraparound. So correct. So it's basically, it acknowledges what you basically do with the data, what is the data itself, and where do you do this. So it basically helps you annotate them with some properties and some metadata, and those are used for standard data management functions, the functions that we talked about a few slides ago. All right. So we'll come to that in a minute when we discuss the architecture. All right. So it's fairly lightweight, and you don't need to do installation. Just to quickly answer that question, you don't need to install it anywhere besides a single host. So I'll go over that in more detail. So core features that Falcon today provides is it has this ability to do pipeline processing. So the DAG that I was showing you, it kind of allows you to process it in that fashion and manage the dependency. It allows you to replicate data between one data center and another data center, one cluster and another cluster, cross colo, within colo, whatever, right? So it can do data retention. It can throw data that is old, that is aged. You can throw it out, or you can kind of even do optionally other things, but those are open for extension but not implemented yet. A single process may not be a DAG. So if your overall process is not DAG, then essentially you are talking about your entire cluster having only one data set that is coming in, and it is producing only one thing. And if you have multiples of them, they are completely unrelated. If that's quite unlikely. I have not come across a situation where in an organization you have distinct data sets coming and they have no reason to be working together. If I were to, so essentially let's say data D1 comes, D2 comes, D3 comes, D1 produces D4, D2 produces D5, and D3 produces D6, and they have nothing to do with each other, then you don't have a DAG, they are just direct lines. So even then you can represent that flow using this notation, but the power of all these features that we talked about becomes very insignificant. It's not great, but it will be very difficult to even imagine a situation where that would be the case, where there are 3 sets of data coming, they are completely unrelated in a single organization, because normally different sets of data that come in your organization are in some ways or form have to be used in conjunction with each other to produce something, and there is a natural pipeline of sorts or DAG of sorts. So if indeed that was the case, I would be very interested to know where and how it would be, but I haven't come across one. So then there is a simple XML based description of these entities that the system accepts these clusters or data sets or processes. They have this native capability to all the data lifecycle functions such as retention, replication, etc. So once the entity definitions are set up and submitted to the Falcon system, it will kind of start the orchestration process. We'll come to that in a bit when we go over the architecture, but quickly we'll cover the features that there are. Then it has this ability to specify retry logic and delay handling. I can say retry this many times with this policy of retry, let's say exponentially back off, or keep repeating every hour, but do one finally at this time and don't try afterward, or permanently fail after that. Or you can say, if upstream data is changing, watch for change every hour. If there was a change upstream, go and rerun your process. Or you can say, keep watching it upstream every hour and finally at this time, and after which don't bother watching. So you could kind of annotate your process definition with these simple declarations, and system would kind of enact them as a rule, if you will, simply treating them as rules. So system has ability to provide monitoring, alerting and management capabilities. The entire system is built on REST API, so it has a client library that you could use. You could use CLI, or you could do a simple authentication and then kind of do a REST based integration as well. It's got Kerberos security enabled on it if you enable the security, otherwise it's unsecure. So we'll come to that question on where exactly is it deployed and how it's deployed. The Falcon system internally uses Oozie for all its orchestration. So when an entity is submitted into the Falcon system, it converts that and rewrites them into Oozie coordinators and Oozie workflows with enough instrumentation around the user's action with its own own action, and submits them into Oozie and watches those Oozie processes on a continuous basis through daemon threads here. So the user's workflow is decorated with some post-processing, pre-processing steps that allows Falcon to watch what's actually happening in the actual application. So before the application, some decoration is done before and after, and those decorated steps uses JMS to notify the Falcon server back in a durable way what's actually happening with the user's action. So that is then used by the Falcon system to figure out what is happening with the user action and starts enacting them. For example, you have said run this only when today's data becomes available. That is converted into specific rules in Oozie, and then using Oozie it will schedule that on the Hadoop cluster. And before and after the jobs are run, it has these post-processing and pre-processing hooks that tells Falcon that should there be a failure, it will notify Falcon that there is a failure. The Falcon, based on the retry policy, will go and retry them. It will keep doing that. For example, on the data set you have defined what is the expected SLA. Because upon successful completion of the workflow in Oozie, it would have gotten a notification saying when it is done. If it has not gotten the notification and the ETA has already elapsed, it knows that this data is going to fail its ETA today or SLA today, and you could alert based on that. Let's say I have set a rule saying that delete this data after 3 days of its arrival. So the Falcon system creates an internal workflow to Uzi, asking that to be run every day, checking whenever data becomes older than that, go and nuke it away, right? So it puts all these things completely hidden. So the Uzi system is not visible to the end user. So the end user is simply working with Falcon through its abstraction and its entity management and instance management functions to complete whatever was required. So we could spend a little time discussing this in more detail. I don't want to gloss over all the details. If you're interested, we can spend some time. If you have any. Yeah. So what's actually happening is that let's take a feed definition for instance. So we have a data set which says this is let's take the original example that we were looking at, that social app, right? Let's say visits data. So it comes every minute into the cluster, and I have a rule saying whenever the data is more than a day old, delete it. So based on that rule, what Falcon would do is it will create a Uzi coordinator, submit it to run every day, and whenever it runs, it looks for data older than a day, and if it finds anything, it will just go and do a file system delete action, and then when it is done, it notifies Falcon saying that the deletion is completed. When the deletion is completed, Falcon can then record saying in its system saying that data is no longer present and it is kind of gone. Now the same input data could be used in a process which is using the data to produce, let's say, today's visit summary, unique users for today. So what the Falcon system then is doing is it takes the input data and then kind of passes that to a Uzi coordinator and say gate on all these inputs, and whenever data becomes available, run them every day at this specific kind of time. So Uzi will run that. Before and after the execution, the system has the pre-processing step and the post-processing step. The pre-processing step essentially is basically saying what's the input size and checksums and stuff like that. It records that so that it can be used for late handling or change data management later. So before it runs a job, it records what is the input state of the input and maintains that state internally. Whenever the time for it to check again if the data has changed, it uses those checksums and lengths of the file and size of the file to see if data has indeed changed. If it has indeed changed, then it will trigger a rerun of that workflow and repeat the user action completely all over again. So that's what it basically does. So most of the work right now is kind of delegated to Uzi. So as we speak, what's actually happening, the Falcon community is voted in favor of moving out of Uzi for some of these functions, starting to build something natively inside Falcon to expand on the gating and scheduling capabilities much beyond what Uzi's capabilities are today. So there are some limitations in what Uzi does today, so we're kind of going away with that. Sorry. So what is exposed from Uzi to user? For example, you saw this thing that we were describing here, right? So you can describe your application and library, right? This application need not just be a cascading flow or a pick flow. Actually, I can give a Uzi workflow XML here. So the entire power of the Uzi workflow abstraction is available and can be used as an application. So for Falcon, Uzi workflow is an application. So it says, okay, I'll run your entire workflow. I will not limit you in any way. So your workflow could be a singular application, which is a MapReduce application, or it could be a pig application, or it could be a Spark application, it could be a cascading application, or a Uzi workflow. So you could do pretty much anything you want. You had a question? So right now, today it is depending on Oozie for the scheduling. It is depending on that. So what we are going to do away is to remove that dependency from Oozie for scheduling, and Oozie in that case becomes just a application engine for us to launch workflows. So if you are defining a Oozie workflow based application, it will use Oozie for launching that and nothing beyond it. So it can be fitted. So the new one of the new primitives that we are planning to expose when Falcon has native scheduling is to allow users to express the fact that watch on this data, give me only what has changed. Okay, so that's a capability that that is being proposed as one of the things that to build inside that. And that's very challenging for us to build inside Oozie. So hence we have chosen to kind of build some of these capabilities natively into Falcon. Now the unit at which it will check for change is essentially at a partition level and not necessarily at an individual record level. It doesn't have an ability to open up a file and find out what has changed, right? So it essentially operates at a partition level. So tables can be partitioned either on file system or on hcatalog or wherever, and it will consider these partitions as unit of data. So a partition is atomic for all practical purposes. So let's say a time partition has changed, then it will basically say this is changed and then you can use it. Or any other, the unit of watching a change would still be at a partition level and not at a record level, because it doesn't have the ability, the lineage of what has been processed and what is new at a record level is far harder to make when you're talking about 50 billion records that you have to consider as the input set, because that becomes very overwhelming for this system to handle. So today the integration with the external data source is fairly weak in Falcon. So we are opening up the lifecycle extension. So there are some patches available from some contributors to integrate with through Scoop. So you could use Scoop to download, let's say, data from a database or sorts, or you can upload data into a database and stuff like that. Scoop is one way through which you could do that. But that patch is available but not committed into trunk. The reason why it's not committed into trunk is in the larger scheme of things we are looking to change the scheme that's being used for these kind of external ingestions. So so that is not aligned, the patch is not aligned with that. So that's where it is right now. Which solutions? Right. Right. So if there are native Hadoop connectors for it to write data into the Hadoop once it ingests, you should be able to look at that and review it. So it's not looked at it yet. So we are trying to open up the life cycle for people to choose how they want to bring the data in. The camel could be a way to do it. So I think we went over how the scheduling kind of happens. So Falcon also operates in a distributed mode. So if you have data centers, multiple data centers, there is this small veneer called Prism, which does a proxy of sorts to give you a global view of what's actually happening in the in your entire organization. So if you have a East Coast data center, a Asia data center, and a Europe data center, each of them running their own Falcon instances, you could use a global catalog and have that in one central place, and that would be able to kind of give a consolidated view of what's actually happening in the entire organization. So it kind of gives you that. So it's a very, very small proxy. Independently, the Falcon servers are quite competent to do everything. Once it's set up in distributed mode, the only limitation is all entity submissions have to happen through this system only. They will be locked down in this. Other than that, all other capabilities are present in the individual Falcon servers. So we'll quickly go over the case study. Apparently only 8 minutes are left, so I'll try and go over this quickly. So I'll bring up a case from InMobi. Quite familiar with what we do at InMobi and how Falcon is being used. So InMobi, a quick view is it's a mobile ad tech company. It's one of the largest independent ad companies out there on the mobile platform. It's got more than 1 billion users. It does a lot of ad requests a day, something in the order of 150, 140,000 ad requests per second. In a single day, we run anywhere between 200 to 250,000 Hadoop jobs in a single day. 25 terabytes of new data we kind of ingest, and 7 terabytes or 7 petabytes of storage. Our data stack comprises of Hadoop, HBase, Zookeeper, Cassandra, Scribe, Fig, Falcon, Oozie, Hive, Lens, and Spark. So essentially, most of the stuff that happens in InMobi at the end of the day, from a data management standpoint, is essentially managed through Falcon. We have 1,000 distinct data sets at InMobi. So these are distinct data which has different schema used for different purpose, and we have about 500 processing applications which uses this. These 500 applications, some of them run very, very frequently, like a minutely. Some of them run less frequently, like a day. Some of them even run once a month, stuff like that. So just to take one use case, so if you have a mobile app, occasionally, let's say pick NDTV for instance, right? So you open up the app, you'd see an ad in the bottom. So that is an ad request that's coming to InMobi. You get this ad request, and that request is kind of recorded into the system as a ad request. And if when we get the ad request, we have a suitable ad for the user based on what we know about the user, we may send an ad back. And that ad, if it is actually rendered on the device, maybe the ad was coming back and the user moved out of the app, then the ad will never get rendered, never be visible. So if the ad is indeed rendered and visible to the user, it sends an event back saying that user has seen the ad. So the user clicks the ad, you'll get another event, and that comes back to the data center. Let's say the ad is has a proposition for you to, let's say, do a Facebook like on something, and if you indeed do a Facebook like, then that would be a conversion event, and that will come through. So all these events are basically collected in different data sets, if you will, streaming continuously, appearing as minutely in minutely buckets, and this data is picked up every hour, summarized, and you generate an hourly summary. And this is actually happening in 5 data centers, or 4 data centers rather, simultaneously, and each of the data centers will collect this data, aggregate them, and the collected aggregates then are shipped to a central place for you to do it. Because the raw data themselves are very, very large, kind of concise them in simple aggregates and send it to a central location for the data to be visible to the consumers faster, right? So this is one kind of use case. I'll take no more than 3-4 minutes to quickly go over the this one. So this is how the cluster definition this case looks. Let's say it's US East is the co-location, and let's say it's New York City. So you define how your read interfaces and write interfaces, and this is how the infrastructure element in Falcon is simply described. Then let's say there's a similar data center in Ireland. Let's say it's Dublin, and you have corresponding things specified there. Then let's take the visits data for a minute, and this is how the description will be looking. So it's categorized into something called traffic. It's appearing minutely. It's available on this cluster and this cluster from this time, which is different. Evict this data after 24 hours, and then you say where the data is present in each of these clusters, and then you can say what the schema is for this. So you can simply describe your data this way. So, and then once similarly you can define, let's say, another stream called interactions. You define that similarly like what we saw in the visits. Now let's say we are taking visits and interactions and then joining them. So the process definition which collects them and joins them will look something like this. So you can say in which clusters do you want to do this concurrently, what's the parallelism that you want, what's the frequency at which you want to run it, what are the inputs that you want to consider for this, and what's the application that you're going to use to kind of run this. So you write your pick script, you define your data set, you define your SLA on the data set, and you submit them. Things would just happen. So this would also be very interesting to look at. This is a case where this is the traffic summary that is produced by the global individual data centers. You can simply say this is one type, this is another type, this is partitioned by the colo, and they all are merged into a central colo. So data will automatically merge. You simply declare them, saying here is my data, here is what I want it to be done as far as movement is concerned, as far as eviction is concerned, as far as archival is concerned. Here are the gating logic in the process definition with respect to this data. You kind of specify this, things would kind of start happening automatically through the Falcon system. So I'm kind of having to rush through, so because I don't have time. Are there any questions? I'd happy to share the example somewhere. I think some of these examples are already there on the public Git for you to kind of look. gitapache.com/Falcon. You should be git.com/Apache/Falcon. You should be able to find these examples there. So some of these entity definitions, all these entity definitions can be done in UI. The UI is built very recently. It's coming in the next release, which is RC is already available. It's being verified for licensing issues. Once that is done, the release should be out in a week or so. So that has entity definition UI, lineage UI, and instance management UI. So you should be able to do some of these stuff through UI. Exactly. So all that can be done through that. So if you have the dev list is very active. So any questions, people will be jumping in and answering. You can write to me as well if you have any questions. That's